Right now, we live inside one of the largest cosmic voids ever discovered, a hollow region of space roughly 2 billion light-years across. Astronomers confirmed its existence in 2013. Most people still have no idea. This hollow isn't just an empty patch between clusters. It's a massive spherical underdensity where matter is about 20% thinner than the cosmic average. And our galaxy sits almost exactly inside it. That matters more than it sounds, because this underdensity bends how we measure the universe. Light travels through weaker gravity here. Space expands faster here. The numbers we observe from galaxy redshifts to the Hubble constant are biased by our position. This discovery began with a simple question: why are there fewer galaxies near us than expected? Astronomers counted tens of thousands of them and found a systematic deficit in every direction. What they mapped was a structure so large that it shouldn't exist according to standard cosmology, yet it does. This is the KBC void, a cosmic desert surrounding everything we call home, and it may be quietly warping our view of the entire universe. The first sign came from a galaxy census. In 2013, astronomers surveyed more than 35,000 galaxies. No matter where they looked, the count was short by about 20%. This wasn't a small statistical blip. The deficit stretched across a region nearly 1 billion light-years wide. Galaxies were simply missing compared to what standard cosmology predicts for such scales. The survey combined multiple wavelengths and methods: optical catalogues, redshift measurements, and infrared checks for obscured galaxies. Every technique pointed to the same result: the space around us is underdense. This structure was soon named the KBC void after the three scientists who confirmed it: Keenan, Amy Barger, and Len Cowie. According to the data, the average matter density inside this region is only about 80% of normal. That difference is huge on a cosmic scale. A 20% gap means weaker gravity, slower structure growth, and a faster local expansion. Simulations show that a void this large should be extremely rare, less than a 1 in 1,000 chance in standard models. Yet we live inside it, and the fact that our own galaxy sits near its center makes every measurement we make more complicated. This isn't just a background detail. It's the environment shaping the numbers we build cosmology on. This was the moment when a quiet anomaly became a serious problem for modern astrophysics. The KBC void is not a distant anomaly. It surrounds us. Our galaxy sits roughly 200 to 400 million light-years from its center, well within the underdense region. The void itself stretches nearly 1 billion light-years in radius, making it one of the largest known structures of its kind. Unlike the empty vacuum of deep space, a cosmic void still contains matter, but its density is drastically lower than the cosmic average. If a typical region of space holds 10 galaxies in a given volume, this region holds maybe 2. Those galaxies are scattered like lonely islands in a dark ocean. There is less gas, less dark matter, and fewer gravitational wells. That means fewer galaxy clusters, slower star formation, and weaker large-scale gravity. In this kind of environment, dark energy becomes the dominant force. Gravity can't balance it here the way it does in dense cosmic walls or filaments. This difference isn't theoretical. Observations show that voids expand faster than the cosmic mean. Over time, they push outward, making their boundaries sharper and their interiors even more sparse. The KBC void is no exception. Galaxies near its edges are already moving away faster than Hubble flow alone would predict. We are part of that motion. Our galaxy drifts outward at roughly 600,000 miles per hour, carried by the gravitational pull of denser structures outside the void. This velocity is measurable, and it matches the pattern expected from a large underdensity. This position is not a coincidence. It affects every observation we make, from supernova distances to background radiation. We are not looking at the cosmos from a neutral vantage point. We are looking from the inside of a cosmic hollow, and that changes everything we measure. The discovery of the KBC void didn't come from a single telescope. It came from consistency across independent surveys. Astronomers first noticed the galaxy deficit in wide-field redshift catalogues. Then radio surveys confirmed the same pattern tracking neutral hydrogen across hundreds of millions of light years. Infrared observations ruled out the idea that dust was hiding distant galaxies. No matter the method, the result held. The volume around us contains about 20% less matter than it should. The data matched a roughly spherical underdensity with our galaxy close to the center. That combination, size, shape, and position made it almost impossible to explain away as coincidence. Next came simulations. When cosmologists modeled structure formation using standard lambda CDM physics, they rarely produced voids this big. Statistically, a KBC-sized hollow requires extremely unusual initial conditions, something like a 10 sigma deviation from average density. That's so unlikely that many simulations never generate one at all. Yet the sky said otherwise. The surveys aligned too cleanly to ignore. A genuine underdense basin existed and we were living inside it. This realization forced astronomers to revisit a key assumption in cosmology, that on large enough scales the universe is uniform and our location is typical. If that assumption fails, then measurements made from inside this basin may not reflect the universe as a whole. They reflect our neighborhood. What started as a technical mapping project had revealed a structure that standard theory struggles to explain. It was the beginning of a cosmological headache that hasn't gone away. The discovery of the KBC void didn't come from a single telescope. It came from consistency across independent surveys. Astronomers first noticed the galaxy deficit in wide-field redshift catalogues. Then radio surveys confirmed the same pattern tracking neutral hydrogen across hundreds of millions of light years. Infrared observations ruled out the idea that dust was hiding distant galaxies. No matter the method, the result held. The volume around us contains about 20% less matter than it should. The data matched a roughly spherical underdensity with our galaxy close to the center. That combination, size, shape, and position made it almost impossible to explain away as coincidence. Next came simulations. When cosmologists modeled structure formation using standard lambda CDM physics, they rarely produced voids this big. Statistically, a KBC-sized hollow requires extremely unusual initial conditions, something like a 10 sigma deviation from average density. That's so unlikely that many simulations never generate one at all. Yet the sky said otherwise. The surveys aligned too cleanly to ignore. A genuine underdense basin existed and we were living inside it. This realization forced astronomers to revisit a key assumption in cosmology, that on large enough scales the universe is uniform and our location is typical. If that assumption fails, then measurements made from inside this basin may not reflect the universe as a whole. They reflect our neighborhood. What started as a technical mapping project had revealed a structure that standard theory struggles to explain. It was the beginning of a cosmological headache that hasn't gone away. In the standard cosmological model, a void as large as the KBC should be almost impossible. Simulations show that the probability of such a deep billion light-year wide underdensity forming by random fluctuations is less than 1 in 1,000. Most simulated universes contain many small voids, some medium ones, but almost none this big. That rarity is what makes this discovery so disruptive. If our cosmic neighborhood is this unusual, it means either we are living in an extremely improbable location, or something in our models is incomplete. Both options are uncomfortable for cosmologists. The size of the KBC void isn't just a bit larger than average. It pushes beyond the expected tail of the probability curve. In simulations, voids typically span a few 100 million light years. Reaching 2 billion requires exceptional conditions in the early universe. It also means this structure influences everything around it. Large voids don't behave like empty boxes. They interact with their surroundings, altering velocities, deflecting light, and affecting local expansion. The larger the void, the stronger these effects become. The KBC void stands out because it sits precisely where we measure much of the data used to calibrate the universe's expansion rate. If we lived in a more typical region, our observations might look different. Instead, we are measuring the cosmos from inside an outlier. This is why the KBC discovery didn't stay a footnote. It became a central piece in one of the most important scientific puzzles of the decade. The KBC void isn't just a curiosity. It collides directly with one of cosmology's core assumptions, that the universe looks roughly the same on sufficiently large scales. This principle, homogeneity and isotropy, is what allows scientists to model the cosmos with simple equations. A structure this large pushes that assumption to its limit. In most simulations, density variations smooth out beyond a few 100 million light-years. The KBC void stretches nearly 3 times farther. That makes it one of the most extreme local environments ever measured. Its depth, about 20% below average density, adds to the tension. If our location is truly this atypical, every cosmic measurement we make must be carefully corrected. Distances derived from redshift velocities of nearby galaxies, even the inferred age of the universe, can all be skewed. Our numbers might not be wrong, they might just be local. This is where the puzzle becomes more than statistics. When a structure is too large to be common but too consistent to be ignored, it forces theory to bend. Either the KBC void is a rare accident, or the models describing how the universe formed are missing something. That's why the discovery of this hollow sits at the center of debates about cosmic expansion. It touches not just mapping surveys, but the foundation of how we understand the shape and history of the universe itself. The KBC void isn't just a structural anomaly, it offers a possible explanation for one of the biggest crises in modern cosmology, the Hubble tension. This is the conflict between 2 precise measurements of the universe's expansion rate. One comes from the early universe using the cosmic microwave background. The other comes from nearby supernovae. The two disagree by about 9%. The early measurement relies on ancient light and physical models of the universe's first moments. It gives an expansion rate of roughly 67 kilometers per second per megaparsec. The local measurement based on supernova distance ladders gives about 73. Both are highly precise. They should match. They don't. If our galaxy is sitting inside a massive underdense basin, that difference makes sense. In a region where gravity is weaker, galaxies drift outward faster than average. Light experiences less gravitational pull and the local expansion rate appears higher. This isn't speculation. When cosmologists simulate how a void of this size would affect nearby galaxies, the extra velocity matches the gap between the two measurements almost exactly. The numbers line up. The void doesn't solve every detail of the Hubble tension debate, but it offers something many other explanations don't. It's based on a real measured structure, not hypothetical new particle or modified physics. That makes it one of the most grounded explanations on the table. Here is the mechanism in one line. Inside a low-density basin, gravity pulls less, so the local Hubble flow looks faster. That single fact can nudge every distance and velocity we measure. In regions with average matter, gravity partly counteracts expansion. Inside a sparse region, there is less matter to slow anything down. Galaxies feel a weaker inward tug and acquire a small extra outward drift on top of the universal expansion. Astronomers call that extra drift a peculiar velocity. It is not space stretching. It is motion through space because of surrounding mass. Picture the mass distribution as a broad bowl with walls made of filaments and clusters. The inside is underfilled. Gravity points toward the walls, not the center. For galaxies inside the basin, the downhill direction is outward. Add that coherent outward motion to the ordinary expansion, and you infer a higher local expansion rate. This effect is distance dependent. Near the basin's middle, the outward drift is strongest. Closer to the boundary, it weakens as the density rises. Far beyond the boundary, the drift fades into the cosmic average. That gradient creates a prediction you can test. The expansion rate inferred from nearby traces should appear a little larger and should decline toward the global value as you use more distant traces. Observations follow that pattern. Supernova measurements anchored within a few 100 million light-years tend to yield a higher number. As samples include events farther out, the inferred rate steps down. The change is not huge, but it is consistent with what a large underdense region would imprint. Crucially, this explanation does not require exotic physics. It uses standard gravity and the measured mass distribution. The only unusual ingredient is our address. If we lived inside a dense wall instead of a hollow, we would infer the opposite, a slightly slower local expansion. So the question turns practical. How do we separate motion caused by the basin from the pure stretching of space? And how far out do we need to measure before the bias becomes negligible? The next part lays out the observational plan. If a massive underdensity surrounds us, its effect should not be random. It should appear in how the measured expansion rate changes with distance. The logic is straightforward. The closer we are to the center of the hollow, the faster galaxies seem to drift away. The farther we look, the weaker that extra velocity becomes. This creates a measurable pattern called a distance-dependent Hubble gradient. At nearby distances a few 100 million light-years, the expansion rate looks a bit higher than the cosmic mean. At intermediate distances it declines, and at very large scales it settles to the global value measured from the early universe. Astronomers have already observed this trend. Supernova surveys show a small but clear step down in the inferred Hubble constant as the sample volume grows. This matches exactly what would happen inside a basin like the KBC void. It is one of the strongest observational hints that the void's influence is real. This gradient is also useful. If we can map it precisely, we can estimate both the depth and size of the hollow without relying on galaxy counts alone. It turns the environment around us into a kind of cosmic laboratory, revealing its structure through the motion of galaxies. But this test has limits. Beyond a few billion light-years, the void signature becomes faint and blends with other large-scale structures. To confirm it, astronomers need multiple overlapping measurements, not just one method, but many reinforcing the same signal. This is where other cosmological probes enter the story. The next step is to look at how ancient light itself reacts to this hollow. The cosmic microwave background of the oldest light in the universe gives us a way to test whether the KBC void is more than a local curiosity. When photons from this ancient radiation pass through regions with different densities, they gain or lose tiny amounts of energy. This is called the integrated Sachs-Wolf effect. In an overdense region, gravity wells can trap photons slightly, making them lose energy on the way out. In an underdense region, the opposite happens. Photons pass through a weaker gravitational field, so they leave with a small energy boost. When measured across the sky, these boosts show up as subtle temperature variations in the background radiation. If the KBC void is real and as deep as surveys suggest, it should leave a faint but measurable imprint on the microwave background. Its position and size align with the kind of low-level signal that sensitive instruments can detect. Multiple studies have already reported such anomalies. While no single detection is decisive, the pattern is consistent with the presence of a large nearby underdensity. This means the void is not only seen in galaxy counts and peculiar velocities, but also hinted at in the oldest light we can observe. That overlap is crucial. It links a local structure to a cosmic scale observation, bridging the gap between modern galaxy surveys and the relic radiation from the early universe. And it gives scientists a powerful way to cross-check the void's properties with independent data. The most powerful part of the integrated Sachs-Wolf effect is not that it reveals a single void. It shows how local structures interact with the oldest light in the universe. By stacking multiple regions across the sky, astronomers can detect the faint signatures left when CMB photons pass through areas of lower density. When researchers applied this method to the regions surrounding our galaxy, they found a weak but consistent signal. The temperature shift was small, only a few millionths of a degree. but it lined up with the predicted position and size of the KBC void. This is exactly what an underdensity of this scale should do to passing photons. This signal does not prove the void alone, but it provides an independent confirmation that light from the early universe feels the structure we live in. The effect cannot be explained away by dust or instrumental noise. It appears in multiple datasets collected with different instruments. The fact that a structure mapped by local galaxy counts also leaves an imprint on the CMB makes the case far stronger. It shows that this hollow is not an artifact of survey design. It is part of the real cosmic landscape, large enough to tug on galaxies, shape redshift measurements, and nudge ancient light. The next step is to look at another line of evidence: the collective motion of galaxies, also known as bulk flows. Another way to test the KBC void is to measure how galaxies move on very large scales. These coordinated motions are called bulk flows. In a perfectly uniform universe, random velocities should cancel out at large distances, but they do not. Observations show that entire groups of galaxies drift together toward denser regions of space. Our own galaxy is part of this pattern. The local group moves at roughly 600,000 miles per hour relative to the cosmic microwave background. This is not due to expansion alone. It is the result of gravitational attraction from structures outside the hollow we live in. The basin pushes us outward while massive clusters and filaments beyond it pull us in. When astronomers map these velocity fields, they find a pattern that fits well with a large underdensity near the center of the flow. Galaxies inside the basin show a coherent outward drift, while galaxies outside point toward massive attractors farther away. This combination explains both our velocity and the gradient measured in other systems. The existence of such a strong bulk flow is one of the clearest dynamical fingerprints of the void. It connects the underdensity to the actual motion of matter in space, not just to how light travels through it. This kind of measurement also provides another way to estimate the depth and shape of the hollow. Velocities trace mass distribution directly, making them a critical piece of the puzzle. Galaxy velocities are not the only clue. By combining redshift surveys with velocity maps, astronomers can reconstruct the mass distribution of the local universe in 3 dimensions. This process reveals the shape of structures that cannot be seen directly. When applied to our cosmic neighborhood, the result is striking. A wide low-density basin with walls made of filaments and clusters surrounding us on all sides. This structure is not perfectly spherical, but it is roughly symmetric. Its center aligns closely with the position of the local group, and its walls stretch out to nearly 1 billion light-years. The boundaries correspond to regions of higher galaxy density, where massive filaments connect to larger structures. Inside the basin, the velocity field shows smooth outward motion. Along the walls, galaxies begin to converge toward distant attractors. This pattern matches what theory predicts for a large, gravitationally quiet region surrounded by denser structures. What makes this mapping powerful is its independence. It does not rely on counting galaxies alone. It uses their motion to infer the gravitational landscape, and that landscape tells the same story as the galaxy counts and the microwave background. We live inside a hollow. The consistency between these methods has made the KBC void one of the most studied local structures in cosmology. But it also raises a deeper question. How does such a rare structure fit into a universe that is supposed to be statistically uniform? In a statistically uniform universe, our position should be ordinary. But the KBC void is anything but ordinary. According to standard cosmological models, the chance of finding a basin this large and this deep near our location is less than 1 in 1,000. That low probability is what turns the void from a local detail into a cosmological puzzle. Voids of this scale are expected to exist, but they should be extremely rare and randomly distributed. The odds of being inside one and not just near its edge are even lower. It is like living exactly at the bottom of a valley in a landscape that is mostly flat. That placement has consequences for how we measure everything around us. Some researchers argue that improbable does not mean impossible. In a universe with billions of observable volumes, even rare events can happen somewhere, but if our location is indeed statistically special, then cosmologists must ask whether that uniqueness is biasing their measurements. This is why the KBC void sits at the center of debates about the cosmological principle. If we live in an unusual region, some of the quantities we think are universal, like the expansion rate, may actually be local. This does not mean the models are wrong. It means the context of our measurements matters more than we once thought. The puzzle is not just about the void itself. It is about whether our cosmic address is skewing our view of the universe. The KBC void challenges a cornerstone of modern cosmology, the cosmological principle. This principle states that the universe looks the same everywhere on sufficiently large scales. It is the foundation behind almost every equation that describes cosmic expansion. If we live inside a rare massive underdensity, then this assumption may not hold exactly where we stand. Most tests of the cosmological principle rely on the idea that local fluctuations average out beyond a few 100 million light-years, but the KBC void stretches much farther. Its size alone pushes the boundary of what is considered large enough to ignore local effects. If this principle fails locally, the consequences ripple outward. Distance measurements, redshift interpretations, and inferred cosmological parameters may all be affected. It does not mean the universe stops being homogeneous on the larger scales. It means our local environment may not reflect that average. Several researchers have proposed that the KBC void provides a real-world test of this principle. If independent measurements from multiple tracer galaxies, supernovae, microwave background and velocities all confirm the same structure, it would show that local deviations can be stronger than expected. The debate is not about whether the cosmological principle is true in general. It is about whether it applies cleanly at our location, and that makes our position in the universe more important than cosmologists once believed. The standard model of cosmology assumes that local irregularities smooth out at scales larger than a few 100 million light-years. This is what allows simple equations to describe the entire universe. But the KBC void pushes that assumption to its limit. A structure nearly 1 billion light-years across is not something that averages out easily. If our position inside this underdensity really matters, then some of the key parameters we infer may not be purely global values. The Hubble constant, the density contrast even estimates of dark energy could be slightly skewed by our location. This doesn't invalidate the models, it simply means they need to account for where the measurements are made. Simulations confirm this sensitivity. When cosmologists model a universe with voids of similar size, they find that observers inside them consistently infer a higher local expansion rate and slightly different values for other parameters. Observers outside these voids, however, measure numbers much closer to the global average. This difference highlights a subtle but important truth. The cosmological principle is not a law of nature, it is a working approximation. And like all approximations, it has limits. The KBC void may be the structure that shows us exactly where those limits begin. Recognizing that limit doesn't break cosmology, it refines it, and it could explain why some of our most precise measurements do not perfectly agree. Not all voids are created equal. Most of them are small, spanning only tens to a few 100 million light-years. These are common features of the cosmic web carved out as gravity pulls matter into filaments and clusters. Voids on this scale are well understood. They are everywhere. But the KBC void belongs to a different class entirely. Its radius stretches close to 1 billion light-years. Structures this large are statistically rare and dynamically powerful. They can influence galaxy flows far beyond their boundaries, bending local measurements of the expansion rate and imprinting signals on background radiation. Astronomers classify voids by both size and density contrast. Small voids cause mild effects, barely shifting velocities. Intermediate voids can produce measurable flows but remain local phenomena. Giant voids like the KBC are game changers. Their scale is large enough to challenge how we apply cosmological principles in practice. Mapping voids of different sizes has become a key part of testing the standard model. If large underdensities like this one are more common than expected, it could hint that the early universe produced stronger fluctuations than current models allow. If they remain as rare as predicted, then we're likely sitting in an improbable but not impossible location. Either way, the size of the KBC void places it in the extreme tail of cosmic structure, a natural laboratory for testing how well our equations hold up under unusual conditions. The size of the KBC void is more than a curiosity. It is the key to why its effects are so noticeable. A small void might slightly nudge galaxy velocities. A giant one shifts measurements across multiple independent probes. When something stretches nearly 1 billion light-years, its influence is impossible to ignore. Large voids modify the flow of galaxies well beyond their walls. They distort redshift-based distances, bias the inferred expansion rate, and leave faint imprints on the cosmic microwave background. Their gravitational influence is subtle, but widespread, accumulating over enormous distances. The most striking part is how consistent the signals are. Galaxy counts, peculiar velocities, bulk flows, and CMB measurements all tell the same story. We live inside a large, underdense basin. Each signal on its own could be dismissed as noise. Together they paint a coherent picture of our cosmic neighborhood. This scale also makes the void an ideal test case for precision cosmology. If models can explain all these signals at once, they are probably capturing reality well. If they cannot, something in the models may need to change. The KBC void is not just another structure in the cosmic web. It is a stress test for the assumptions that hold modern cosmology together. Every cosmic void is defined by two numbers, its radius and its density contrast. The radius sets its physical size, while the contrast tells how much matter is missing compared to the cosmic average. For the KBC void, both of these numbers are extreme. Its radius is close to 1 billion light-years and its density contrast is roughly 20% below the mean. This combination matters because it determines how strongly the void interacts with its surroundings. A shallow basin would barely affect galaxy motions, but a deep one alters velocities across hundreds of millions of light-years, producing coherent bulk flows and measurable shifts in redshift-based distances. The boundary between the underdense interior and the denser exterior acts like a gravitational slope. Galaxies near the center experience the weakest pull and move outward fastest. Those closer to the edge slow down as they approach denser filaments. This gradient is what creates the distinct dynamical signature astronomers have mapped. These properties make the KBC void a textbook example of how cosmic underdensities shape their environment. It is not just an empty region. It is an active structure, one that subtly rearranges the flow of galaxies and light. Understanding its anatomy is essential to understanding how it can warp our view of the universe. The edge of the KBC void is not a sharp wall. It is a gradient, a smooth rise in density that creates a gentle but persistent gravitational slope. Galaxies near the center of the basin experience the least gravitational pull and drift outward fastest. As they move toward the boundary, the pull strengthens and their outward velocity slows. This structure behaves like a bowl surrounded by ridges. Matter at the bottom flows outward while material near the slopes encounters increasing resistance. Over billions of years, this differential motion sharpens the boundary, making the underdense region appear more defined even though it was once smoother. This slope also affects how light travels. Photons passing through the center cross a region with weaker gravity, gaining a tiny boost in energy. Those passing through the boundary encounter stronger gravitational fields, slightly altering their paths and redshifts. These shifts are small but measurable with modern instruments. The interplay between the slope and outward motion explains why the void's dynamical signature is so coherent. The pattern is not random. It is the natural outcome of how gravity behaves in a large underdense region. By mapping these gradients precisely, astronomers can learn more than just the size of the void. They can reconstruct its history, revealing how it grew from a slight fluctuation into a structure that now stretches nearly 1 billion light years. Light travelling through the KBC void does not behave the same as light passing through an average region of space. As photons cross the underdense interior, they experience weaker gravitational fields. This gives them a slight energy boost, a subtle but measurable effect. When they exit the void and encounter denser structures, the opposite happens. The change is small, but over cosmic distances it adds up. This is why the boundary of a void is more than just a line on a map. It is a transition zone where photons gain or lose energy depending on their path. This effect is part of the integrated Sachs-Wolf signal detected in the cosmic microwave background. It also contributes to redshift distortions in observations of distant galaxies. In principle, two identical galaxies located at the same distance but along different sightlines, one through the void, one through denser space, would appear to have slightly different redshifts. The difference is tiny, but modern instruments can detect it statistically when many galaxies are measured at once. This is one reason voids have become precision tools in cosmology. They do not just move matter, they shape the light that carries the history of the universe to our telescopes. When astronomers measure the expansion of the universe, they rely on redshift. But redshift is not influenced only by cosmic expansion. Local structures like voids can also leave their fingerprints. Inside the KBC void, galaxies gain a small outward velocity on top of the Hubble flow. This extra motion shifts their observed redshifts, making them look slightly farther away than they actually are. These distortions are subtle for individual galaxies, but they become powerful when measured statistically across large samples. Surveys that map the sky in detail can detect the difference between galaxies sitting inside an underdensity and those outside it. This is why the KBC void can't be ignored when calibrating local distance measurements. The effect is especially important for supernova surveys. Type I supernovae are used as standard candles to measure cosmic expansion. If a large underdensity adds outward velocity to their host galaxies, the inferred expansion rate appears higher than the global value. This mechanism fits neatly with the observed gap between local and early universe measurements of the Hubble constant. Correcting for this distortion does not require new physics. It only requires acknowledging where we are in the cosmic landscape. That's why understanding redshift distortions is essential to turning raw observations into accurate cosmology. Redshift distortions caused by the KBC void lead to a deeper issue: local bias. If our measurements of cosmic expansion are taken from an unusual environment, then they may not represent the global universe accurately. This is one of the strongest arguments for why cosmologists must account for the void when interpreting data. Imagine using a thermometer that always reads a little warmer because it sits next to a heat source. The thermometer is not broken, but the measurement is biased by its location. In the same way, our local expansion rate might be slightly inflated simply because we are sitting inside a low-density region. This bias affects several key measurements. The Hubble constant inferred galaxy distances and even estimates of the age of the universe. Each of these relies on the assumption that our environment is typical. If that assumption fails, the entire calibration of our cosmic yardstick shifts. The good news is that local bias can be quantified. By combining multiple independent probes, supernova velocity fields and background radiation, scientists can measure how much of the discrepancy comes from location rather than new physics. Recognizing this bias does not weaken cosmology. It strengthens it by making sure our measurements reflect the universe as a whole, not just the hollow we happen to inhabit. Every precision measurement in cosmology depends on calibration. Whether astronomers use supernovae standard rulers or background radiation, all of it relies on carefully linking observed redshift to actual distance. If the calibration is biased by local structures like the KBC void, then the conclusions drawn from those measurements can drift, not because the universe is different, but because our perspective is. This is why the local environment must be considered. If we ignore it, we may overestimate the expansion rate, or misjudge how fast galaxies are truly moving away. Even small biases at low redshifts can propagate upward, affecting the inferred value of dark energy density or the universe's age. Fortunately, void-induced distortions are predictable. They follow gravitational physics, not exotic unknowns. That means they can be modelled and subtracted, but only if their structure is mapped accurately. This is where the KBC void becomes more than a curiosity. It is a calibration anchor. By understanding its shape and influence, astronomers can sharpen their measurements and bring local and global observations into better agreement. A more precise calibration may not only ease the Hubble tension, it might also reveal subtler patterns hidden in the data. Our position in the universe is not just a detail, it shapes how we see everything. If we lived in a typical region, many of our cosmological measurements might align more cleanly, but sitting inside a large underdensity like the KBC void means every number we extract from the sky is coloured by context. This is not an error, it is simply how gravity and expansion work together. Modern cosmology relies on extraordinary precision. Tiny differences in redshift velocity or brightness can shift the inferred age composition and fate of the universe. If local structures like the void are not accounted for, they can quietly introduce systematic offsets. Context also affects how we interpret tensions between measurements. What might appear to be evidence for new physics could in part be the result of local structure. Understanding that distinction is essential. It tells us when we're looking at the universe itself and when we're just looking from a peculiar spot within it. The KBC void is a reminder that location matters. It turns the universe from a static backdrop into a dynamic landscape, one that bends both matter and perception. The KBC void does not rewrite the laws of physics. It bends them, gently shifting measurements just enough to matter in an era where cosmology operates on razor-thin margins of precision. A slight outward velocity here, a small redshift bias there. These are not dramatic effects, but they accumulate. And when added together, they can mimic or mask signals that cosmologists might otherwise attribute to new physics. This is why the void has become such a focal point in modern research. It offers a grounded explanation for several puzzles, including part of the Hubble tension, without invoking hypothetical particles or forces. Instead, it relies on well-understood gravitational dynamics. The key is scale. A structure nearly 1 billion light-years wide has a long reach. It subtly reshapes the local velocity field, affects how light moves and biases how we calibrate cosmic distances. All of this happens without violating a single physical law. That is what makes the KBC void important. It is not a crisis for cosmology, it is a correction. A reminder that our vantage point matters just as much as the equations we use to describe the universe. Modern cosmology is built on precision. Tiny differences in observed redshift light curves or galaxy velocities can change the inferred values of the universe's most fundamental parameters. That level of sensitivity means even modest local structures can influence the final results. The KBC void is a perfect example of how environment meets measurement. If we ignored the void's existence, we might misinterpret small biases as hints of new physics. A slightly higher local expansion rate could be mistaken for unknown forces or particles. But once the underdensity is accounted for, some of those tensions ease. It is not that the data changes, the interpretation does. This interplay between local environment and cosmological inference is becoming more important as instruments grow sharper. Upcoming surveys will measure redshifts and distances with unprecedented precision. At that level, even a mild underdensity cannot be treated as background noise. The void turns precision into context. It reminds us that every observation is made from somewhere, and that somewhere leaves its mark on the numbers we trust. Cosmology at the precision frontier is shaped by small effects, a fraction of a % difference in measured expansion. A slight shift in redshift or a tiny energy change in background photons can cascade through calculations and alter the inferred history of the universe. The KBC void is a structure perfectly positioned to create exactly this kind of subtle influence. A large underdensity does not act like a single big force. Instead, it introduces gentle biases across many different observables: galaxy velocities, luminosity distances, bulk flows, and even CMB temperature fluctuations. None of these shifts are overwhelming on their own, but together they build a coherent pattern that changes how we interpret data. This is why researchers study the void so carefully. If these effects are not accounted for, they can amplify or mask signals that appear to point toward new physics. If they are modeled correctly, they help refine our understanding of the universe without inventing new ingredients. The KBC void reminds us that cosmic structures do not have to be violent to be important. Quiet distortions spread across billions of light years can speak just as loudly as explosive events. Cosmic voids are more than just empty regions. Their low-density interiors make them quiet environments, where subtle physical effects can be detected with less interference from crowded structures like clusters or filaments. The KBC void, because of its enormous scale, acts as one of the best natural laboratories for studying how gravity expansion and light interact. Inside the basin, the gravitational landscape is smoother. This allows researchers to measure outward flows, redshift gradients, and Sachs-Wolf temperature shifts with remarkable clarity. These signals would be buried in noise inside denser regions. Instead, here they stand out. The lack of massive structures also reduces uncertainties, turning the void into a clean testing ground for cosmological models. Scientists use this environment to stress test our understanding of expansion. If standard models can reproduce the signals coming from the KBC void from galaxy velocities to background light distortions, it reinforces their validity. If not, the discrepancy reveals exactly where those models may need refinement. The void's calmness is what makes it powerful. It transforms emptiness into precision, offering a place where the universe quietly shows how it works. The KBC void is not just a theoretical idea. This vast underdensity leaves measurable marks across independent datasets, and those marks are consistent. The signals are faint, but they repeat from one method to another, exactly the kind of pattern that makes cosmologists pay attention. Galaxy velocities, supernova distances, and microwave background temperatures all point to the same conclusion. We live inside a low-density basin that subtly lifts the local expansion rate. The first layer of evidence comes from precision mapping. Astronomers chart galaxy positions and line-of-sight speeds across wide areas, then subtract the smooth Hubble flow to reveal peculiar velocities. In these maps, vectors tend to point outward from our neighborhood, with the largest drifts near the interior and weaker motions toward the edge. When overlaid with supernova distances, the same pattern emerges. Nearby samples imply faster expansion, while larger volumes align more closely with the global value. The second layer comes from ancient light. As microwave background photons cross this hollow, they traverse weaker gravity and leave with a touch more energy. Stacked analyses find a faint temperature uptick aligned with the direction and approximate scale of the structure. No single patch of sky is decisive, but the combined signal behaves exactly as theory predicts for a wide, deep basin. The final layer is coherence. Each probe carries its own systematics, yet the independent pictures match. Outward flows, distance-dependent expansion, and a subtle background signature. When different methods converge, the chance of coincidence drops and the case for a real structure grows. This isn't a speculative fix for a theory, it's a measured feature that sets the baseline for how we read the cosmos. Voids may look like nothing, yet that emptiness is exactly why they are powerful. In low-density regions, gravity is weak, foreground clutter is minimal and messy. Astrophysical effects fade away. A basin like this gives astronomers a clean stage to watch how cosmic expansion behaves with fewer interfering factors. When the environment is simple, tiny signals that would drown in clusters can rise above the noise. Inside such a hollow, the density contrast is smooth and predictable. That allows astronomers to measure coherent outward motions and compare them with expectations from standard gravity. If the local expansion appears slightly faster near the interior and relaxes toward the boundary, this gradient can be mapped to constrain the depth and size of the structure. The same region also helps test light-based probes. Photons crossing a shallow gravitational potential leave behind a tiny temperature step that can be detected when many sky patches are stacked together. These voids also enable crucial cross-checks. Weak lensing becomes weak anti-lensing, subtly diluting galaxy shapes instead of magnifying them. Redshift space distortions stretch along the line of sight, revealing the underlying velocity field. Even the acoustic scale used as a standard ruler can be compared inside and outside the basin to test for subtle offsets. The power of this approach is methodological. Each probe comes with its own systematics, but when they all point in the same direction, confidence grows. If models align with the data, the void sharpens our measurements. If not, the mismatch exposes where our assumptions break. In a universe crowded with galaxies, clusters and filaments, empty regions may seem unimportant, but for cosmologists they can be just as revealing as the luminous structures around them. A wide underdense basin like the one surrounding us offers a rare quiet view of how expansion behaves when gravity is weakest. In these hollows, the physics becomes cleaner, and that clarity is what makes them scientifically valuable. This local structure is so large and deep that its imprint appears in multiple independent datasets. Outward galaxy flows, redshift distortions, and faint temperature shifts in the background sky. Each signal alone is subtle, but together they outline a feature that's difficult to dismiss as coincidence. It's not a single measurement that reveals the shape of the basin, it's the convergence of many. By treating this region as part of the data rather than a source of error, astronomers can refine their measurements of cosmic expansion. Low-density environments act like natural laboratories, where gravitational effects are less tangled, allowing faint signals to stand out more clearly. Far from being irrelevant, emptiness sharpens our view of the universe. It reminds us that the spaces between galaxies can teach us just as much about cosmology as the galaxies themselves. When measurements are made from inside a low-density basin, the first challenge is to separate local effects from global truths. The most direct way to do that is to compare observables sensitive to nearby structure with those averaged over much larger volumes. If the two disagree at short distances but align at greater ones, the gap points to the influence of our cosmic neighborhood rather than new physics. Nearby traces form the first step. Type Ia supernova tip of the red giant branch distances and water mesas provide the local distance ladder. These are highly responsive to peculiar velocities and to the slightly faster expansion inside the hollow. To step outward, cosmologists use baryon acoustic oscillations and the acoustic scale in the cosmic microwave background, which cover such vast volumes that local quirks fade away. If the local ladder yields a higher expansion rate than these global rulers, the difference reflects environment, not error. The same reasoning applies to velocities. Flow maps for galaxies within a few 100 million light-years show a clear outward gradient. Extending them to the edges and beyond, the drift weakens and aligns with distant attractors. Redshift and distance measurements together reveal a step-down pattern, exactly as expected from an underdense region. Cross-checks make the picture stronger. Weak lensing reveals a small deficit in convergence redshift space. Distortions show line of sight stretching, and microwave background patches display a subtle temperature step. When these independent signals converge, local bias can be cleanly removed, leaving the global expansion untouched. One of the most persistent puzzles in cosmology is the mismatch between the locally measured expansion rate and the value inferred from the early universe. A large underdense region like the one we live in can explain part of that gap without invoking any new physics. It's not about hidden forces or unknown particles, it's about location. Inside a hollow, weaker gravity allows galaxies to drift outward a bit faster. Light travelling through this region experiences less deceleration, making nearby sources appear slightly farther away. When these observations are used to build the distance ladder, they yield a larger value for the Hubble constant, and at greater distances where the effect fades, the inferred expansion rate returns toward the global number. Even a small outward bias is enough to shift measurements by a few percent, which is significant at today's level of precision. Studies have shown that this contribution alone can reduce the tension between local and early universe results. This doesn't solve the entire problem, but it reframes it. The difference is not only in the data part of it comes from where we're standing in the cosmic web. The mechanism behind the local boost in expansion is straightforward physics. In dense regions, gravity slows motions and pulls galaxies inward. In underdense regions, the opposite happens. Weaker gravitational pull allows galaxies to drift outward just a bit faster than the average Hubble flow. This small difference is precisely what shows up in local expansion measurements. Imagine two identical galaxies placed at the same true distance, one along a line of sight through this hollow, and one through a denser part of the cosmic web. The galaxy inside the low-density region will appear to recede slightly faster. That subtle offset is enough to bias the distance ladder if not accounted for. As the line of sight extends outward, the influence fades. Once it reaches surrounding filaments, the local boost gives way to the gravitational tug of massive structures. The measured expansion then settles closer to the global value. This is why nearby observations consistently yield slightly higher numbers than those tied to distant rulers. Because we are positioned deep within this basin, the outward drift is strong enough to matter for precision cosmology. It's not a dramatic effect, but a quiet, measurable one, and ignoring it would distort the scale of the universe itself. The outward drift produced by our surrounding basin is not theoretical. It can be measured directly. Astronomers track galaxy motions through their redshifts and compare them with the smooth Hubble flow. The difference between the two reveals a coherent velocity field that mirrors the shape of the underdense region around us. The effect is strongest near the interior, where gravity is weakest. Galaxies here show the largest deviations from the expected velocity. Moving outward, the signal softens, and beyond the edge it gives way to the gravitational pull of filaments and clusters. This gradient maps almost perfectly onto the geometry inferred from redshift surveys and velocity reconstructions. These results do not rely on a single dataset. They come from multiple surveys covering thousands of galaxies across hundreds of millions of light years. The agreement between independent measurements is what gives the signal weight. A pattern seen once might be coincidence, but when it repeats in survey after survey, it becomes a physical fact. This is why local underdensities matter. They may be quiet and invisible to the eye, but their fingerprints are written clearly in the motion of galaxies that drift across them. In precision cosmology, even a small bias can shift the entire picture. Measurements of the Hubble constant aim for accuracy at the level of just a few percent. A local boost caused by the surrounding hollow is well within that scale, small enough to go unnoticed at first glance, but large enough to reshape the numbers we rely on. A mild outward drift alters the inferred expansion rate. A faint gravitational gradient shifts redshift distributions. A tiny energy gain in background photons leaves its trace in temperature maps. None of these effects dominate the data individually, but together they push key cosmological parameters away from their true values. That is why local structure plays a central role in the discussion around the so-called Hubble tension. If part of the discrepancy comes from environment, then the amount of new physics needed to explain the rest is smaller. The puzzle doesn't disappear, it becomes more focused. In a field where fractions of a percent matter, ignoring these quiet biases is not an option. They may be subtle, but their reach extends across the entire framework of modern cosmology. To understand why environment matters, it helps to look closely at how bias forms. When light from nearby galaxies reaches us, its redshift carries two signals: the smooth global expansion and a local contribution shaped by the gravitational landscape. In a low-density region, that second component adds a subtle outward drift to the measured velocity. If this effect isn't modelled, it distorts distance calculations. Galaxies appear slightly farther away than they truly are, and the inferred expansion rate rises. The data themselves aren't wrong, the interpretation is incomplete. Recognizing that extra component turns what looks like a mystery into a measurable correction. This bias also reaches beyond redshifts. It affects supernova brightness, peculiar velocity reconstructions, and even temperature patterns in the cosmic microwave background. Each piece of evidence tilts gently in the same direction. The power of the effect comes not from its strength in any single dataset, but from its coherence across many. Because the source of the bias is physical and well-defined, it can be measured, modelled, and removed. That transforms it from a hidden complication into a tool that makes cosmology more precise. When astronomers measure the expansion rate of the universe, they don't simply read redshifts, they process, model, and correct them. One crucial step is removing the influence of local structure. The outward drift produced by the surrounding underdensity is handled just like instrumental noise or statistical uncertainty. It's measured and subtracted. Surveys such as Cosmic Flows 3 map galaxy velocities across hundreds of millions of light years. They reveal coherent flows pointing outward from our region, a signature of the hollow we inhabit. This velocity field is then used to correct distance indicators like Type Ia supernovae or tip of the red giant branch stars. The adjustment is small, only a few %, but at modern precision that is enough to shift cosmological results. The same logic applies to redshift-based distances. By removing the modelled outward boost, the inferred local Hubble, constant moves closer to the value derived from early universe observations. The tension shrinks not because of exotic new physics, but because we've accounted for where we stand. Our location in the cosmic web is not a footnote, it's a measurable factor. And once measured, it becomes part of the calibration that sharpens our view of the universe. For a long time, local structures were treated as nuisances to be averaged away, but with modern precision, astronomers have learned to use them as assets. The underdensity around us isn't background noise. It's a measurable structure that can refine cosmological models when handled correctly. One clear example comes from Sloan Digital Sky Survey. By charting millions of galaxies and combining that information with velocity reconstructions from Cosmic Flows 3 researchers, revealed a coherent outward flow stretching across hundreds of millions of light years. Instead of ignoring this signal, cosmologists fold it directly into their models. This approach allows local measurements of the Hubble constant to be corrected in real time. By treating the flow as a calibration anchor rather than a disturbance, the spread between local and global expansion rates narrows. The structure we live in becomes part of the measuring stick itself. This shift in perspective is subtle but powerful. Precision cosmology isn't about pretending we observe from nowhere. It's about acknowledging exactly where we are and turning that fact into an advantage. The region surrounding us is not an isolated pocket of emptiness. It is woven into the vast cosmic web, a network of filaments, walls, and voids that defines the universe on its larger scales. These low-density regions occupy nearly 80% of cosmic volume, while most matter is concentrated along thin filaments. The underdensity we inhabit is simply one node in this intricate structure. This arrangement emerges naturally from the lambda CDM model. As matter collapses into clusters and sheets, the spaces between them become progressively emptier, forming vast basins with weak gravitational potentials. The hollow around us is especially large, spanning close to 1 billion light-years, big enough to leave measurable fingerprints on local expansion. Its position within the web explains the observed velocity pattern: weak pull at the center, stronger influence at the edges, and a smooth handoff to the gravitational tug of nearby filaments. Beyond those boundaries lie massive attractors that guide the flow of matter. By situating our measurements within this network, cosmologists can separate environmental effects from global behavior. We are not observing the universe from nowhere. We are measuring it from a structured, evolving node within the cosmic web. The low-density basin around us is tightly linked to larger cosmic structures. Its edges connect to filaments that stretch for hundreds of millions of light years, channeling matter toward distant attractors such as the Great Attractor and the Shapley supercluster. These links are what give the local outward drift its place within the grand flow of the universe. Inside, the hollow gravitational pull is weak, allowing galaxies to move outward relative to us. Near the boundary, distant clusters take over, bending those trajectories along the filaments. The result is a smooth transition from expansion inside to infall beyond matching what cosmological simulations of void filament networks predict. Observations confirm this behavior. Velocity reconstructions from Cosmic Flows 3 show coherent streams flowing from the interior toward major attractors in the surrounding web. The alignment between measured flows and known structures is too tight to be coincidence. It's the gravitational fingerprint of connectivity on cosmic scales. By tracing these larger currents, astronomers can place our local underdensity in its proper context. It's not an isolated void, but one component of a vast interlinked network of motion that shapes the universe we observe. To understand our place in the cosmic web, astronomers go beyond simply counting galaxies. They track how those galaxies move. Every redshift contains two intertwined signals: the smooth expansion of the universe and the local velocity produced by gravitational structure. By combining redshift with independent distance measurements, researchers can separate these components and reconstruct the velocity field surrounding us. Surveys like Cosmic Flows 3 apply this technique to thousands of galaxies spanning hundreds of millions of light years. The resulting maps reveal clear outward motion in the interior of the basin, which gradually weakens at the edge and bends along filaments toward distant attractors. This is not a theoretical model but a direct measurement built from real data. To ensure reliability, several distance indicators are used together: Type Ia supernovae tip of the red giant branch, star surface, brightness fluctuations, and water mesas. Each method has its own uncertainties, but when combined they expose a coherent flow pattern that no single dataset could reveal alone. These velocity maps turn a local underdensity from an abstract concept into something concrete. The flow of galaxies itself becomes the proof of the structure shaping our cosmic neighborhood, one of the most delicate clues confirming the presence of our local underdensity comes from the integrated Sachs-Wolf effect. When photons from the cosmic microwave background pass through regions of varying gravitational potential, they gain or lose a tiny amount of energy. A wide, shallow basin like the one around us leaves behind a faint positive temperature imprint on the background sky. The signal is extraordinarily small, just a few microkelvins, but detectable when many sky patches are stacked together. Observational analyses have found a weak temperature rise aligned with the direction and approximate scale of our hollow. The match between this temperature profile and the geometry derived from galaxy surveys strongly supports the reality of the structure. Unlike galaxy counts or velocity fields, this imprint comes from the oldest light in the universe. It is an independent probe that doesn't rely on local distance measurements. If the Sachs-Wolf signature and the velocity maps point to the same feature, the probability of a coincidence drops dramatically. This convergence of evidence, motion redshift, and ancient radiation turns the hollow around us from a hypothesis into a measurable piece of the cosmic landscape. The integrated Sachs-Wolf effect offers a unique advantage. It ties the geometry of nearby structure to the oldest light in the universe. Unlike velocity fields or redshift surveys, which rely on relatively recent data, this signal reflects how the background radiation itself was altered as it passed through evolving gravitational landscapes. That makes it one of the cleanest cross-checks available. When photons travel through an underdense region, they experience less gravitational pull on the way in and out. Because the universe is expanding, the potential well stretches slightly while the photons are inside and they leave with a tiny net energy gained. That extra energy shows up as a small positive temperature fluctuation in the cosmic microwave background. This pattern has been detected statistically by stacking sky regions that align with the hollow surrounding us. Though faint only a few microkelvins, it matches both the direction and scale indicated by galaxy surveys. The agreement between these independent probes reinforces the idea that we're observing a real structure, not an artifact of measurement. Cosmology thrives on converging lines of evidence. When ancient light galaxy positions and velocity fields all point to the same underdensity, the case for its existence becomes remarkably strong. Detecting the integrated Sachs-Wolf effect requires more than a single observation. The signal is far too weak to stand out in one patch of the cosmic microwave background. Instead, astronomers use a technique called stacking, combining data from many regions of the sky that align with known large-scale structures, including the underdensity around her. Each individual temperature fluctuation is only a few microkelvins well below the noise level of a single measurement. But when dozens or even hundreds of sky patches are averaged, the random variations cancel out and the true signal emerges. This method has already been applied successfully to supervoids across the sky, and the result near our location shows the same subtle, positive temperature shift predicted by theory. What makes this approach powerful is its independence. It does not rely on galaxy velocities, redshift distortions, or local distance ladders. The signature is written directly into the oldest light in the universe, offering a clean complementary check on other lines of evidence. This is how modern cosmology works best, not by trusting a single measurement, but by letting many weak signals align to form a clear, reliable picture of the structure we live in. The story of our local underdensity isn't about a single dramatic discovery. It's about many small signals adding up. Each individual observation to a faint outward flow, a tiny temperature fluctuation, a subtle redshift distortion could be dismissed on its own, but together they form a pattern too consistent to ignore. This is the essence of precision cosmology. Rather than relying on one measurement, researchers collect weak but independent clues from multiple angles. Velocity fields reveal motion redshift surveys trace structure, and the integrated Sachs-Wolf effect shows the same signature in the oldest light. When all these signals converge on the same scale and direction, they paint a coherent picture of the basin surrounding us. Such stacking of evidence doesn't just confirm the structure, it also sharpens global measurements. By identifying and correcting for local effects, astronomers can bring the locally measured Hubble constant closer to the value inferred from the early universe. The result is less tension, tighter error bars, and a more reliable cosmic framework. Weak signals can be powerful. When aligned, they become a chorus that speaks clearly about the structure of the universe we inhabit. What makes the case for our local underdensity convincing is not the strength of any single measurement, but the way multiple independent probes point to the same structure. In cosmology, convergence matters more than volume. A faint signal appearing in 3 different datasets is more powerful than a strong one appearing in only one. Velocity fields reveal an outward drift that traces the shape of the basin. Redshift surveys map a matching underdensity. Temperature data from the cosmic microwave background carry the integrated Sachs-Wolf effect that aligns with both. None of these probes rely on the same assumptions or the same instruments. Their agreement is therefore a strong indicator that the structure is real. This layered approach is what allows astronomers to build confidence in delicate results. It's the same principle used to verify the existence of dark energy, or to measure cosmic acceleration. No single proof stands alone, but together they become compelling. Our local environment, once treated as an inconvenience, has turned into a testbed where many strands of evidence intersect. That convergence makes the picture of our cosmic neighborhood sharper and harder to dismiss. One of the most important consequences of mapping our local underdensity is its impact on the Hubble tension. This tension, the mismatch between local and early universe expansion rates, has become one of the defining puzzles of modern cosmology, but not all of the gap may point to new physics. Part of it may simply reflect where we are standing in the cosmic web. The outward velocity field measured in our region slightly raises the locally inferred Hubble constant. When that boost is modelled and subtracted, the value shifts downward, narrowing the gap with measurements from the cosmic microwave background. This doesn't erase the discrepancy entirely, but it cuts it down to a scale more consistent with statistical and systematic uncertainty. The advantage of this explanation is its simplicity. It doesn't require new particles, exotic energy components, or a breakdown of the standard lambda CDM model. It only requires acknowledging the measurable influence of the environment we inhabit. If part of the tension stems from location rather than fundamental physics, then cosmologists can focus on the remaining gap with sharper tools separating what the universe is from where we are inside it. Every measurement in cosmology is filtered through perspective. We cannot step outside the universe to take a neutral reading. We can only observe from within it. That means local structure will always leave some imprint on what we see. The challenge is to separate what belongs to our environment from what belongs to the fundamental laws of physics. If our region happens to be less dense than average, the local expansion rate we measure will naturally run high. This shift is not an illusion. It's a predictable outcome of general relativity. Correcting for that bias brings local observations into closer alignment with the global model. Once that correction is applied, any remaining difference must come from deeper physical causes, not from geography. This distinction is critical. Without it, we risk mistaking a local feature for a universal principle. With it, the data become cleaner and cosmological models can be tested more precisely. The universe doesn't have to change to explain our numbers. Sometimes it's enough to understand where we are standing within it. Perspective may seem like a limitation, but in practice it is a powerful calibration tool, one that turns our local surroundings into a reference frame for the cosmos itself. The Hubble tension is one of the loudest debates in modern cosmology, often described as a potential signal of new physics. But before changing the laws that describe the universe, scientists look inward toward the environment in which these measurements are made. Not every discrepancy points to something exotic. Some arise from where and how we observe. The underdensity surrounding our region creates a subtle outward velocity field. That small boost inflates the locally inferred expansion rate, shifting the Hubble constant upward. When this effect is modelled and corrected, the tension with early universe measurements doesn't vanish, but it narrows to a more manageable gap. This means part of what once seemed like a cosmic mystery may simply reflect geography, not new particles or forces. This logic isn't unique to our case. In precision cosmology, systematics are always checked first from telescope calibration to local flow models before invoking radical explanations. The universe has a way of hiding complexity in plain sight. By separating environmental bias from fundamental signals, cosmologists are not dismissing the tension, but clarifying its origin. What remains after that correction will speak far more clearly about whether new physics is truly needed. Correcting for our location in the cosmic web does not make the Hubble tension disappear. It only peels away the part of the discrepancy that comes from environment. Once that layer is removed, a smaller but persistent gap remains between the locally measured Hubble constant and the value inferred from the cosmic microwave background. This residual difference is what cosmologists now focus on most closely. Several possibilities remain on the table. It could be unaccounted systematic error, small effects from instrument calibration, survey selection, or distance indicators. It could be statistical fluctuation, a rare but not impossible outcome. Or it could hint at something deeper, such as an early universe phenomenon that changed the expansion rate long before galaxies formed. The key point is that this leftover tension is cleaner. By subtracting local bias, the problem is no longer blurred by geography. Whatever remains must either be hidden in our measurements or rooted in fundamental physics. This clarity is what makes environmental corrections so powerful. The story of the tension doesn't end here, but now it can be told with sharper lines and fewer distractions. Once environmental effects are accounted for, the remaining Hubble tension demands an explanation. If local structure doesn't tell the whole story, then the answer may lie in new physics. Several competing hypotheses have emerged, each with its own implications for the history of the universe. One leading idea is early dark energy, a brief burst of additional energy density in the first few 100,000 years after the Big Bang. By slightly increasing the expansion rate early on, it would reduce the inferred age of the universe, at recombination effectively raising the early universe estimate of the Hubble constant. This brings the two measurements closer together, but requires fine-tuned timing and strength to avoid breaking other cosmological constraints. Another possibility involves modified gravity. If the strength of gravity changed subtly over time, the expansion history would shift without invoking new energy components. These models are elegant but face tight limits from large-scale structure data. A third contender focuses on neutrino mass hierarchy. If neutrinos have masses or interactions different from the standard model assumption, they can slightly alter the expansion rate in both early and late epochs. None of these explanations is proven and none fully resolves the tension alone. But they offer distinct testable predictions, and that is where cosmology moved from measuring to understanding. Before invoking exotic physics, cosmologists always start by checking the ground beneath their feet, quite literally. Environmental effects, instrumental systematics, and data selection biases are the first suspects in any precision measurement. This discipline is why the Hubble tension is not treated as a mystery to solve with a single bold idea, but as a layered problem to be peeled back step by step. The underdensity around us is the clearest example of this principle. It's measurable, its effect on the Hubble constant is predictable, and it can be corrected with well-established methods. This stands in contrast to hypotheses like early dark energy or modified gravity, which require changes to the theoretical framework itself. In science, the simplest explanations that match the data are tested first. This is not a dismissal of new physics, it's a roadmap. By quantifying and removing environmental contributions, any remaining discrepancy becomes cleaner, making it easier to test the truly fundamental hypotheses. A puzzle that was once messy and ambiguous turns into a sharper target. In this sense, our position in the cosmic web is not an obstacle but a starting point. It is where the search for deeper answers begins. Correcting for local environment doesn't just make the Hubble tension easier to interpret, it raises the overall precision of cosmology itself. By removing known biases, astronomers can measure fundamental parameters with greater confidence. The clearer the local picture, the sharper the global model becomes. This approach matters even more in the era of high-resolution surveys. Missions like the Euclid mission, the Vera-C, Rubin Observatory and the Nancy Grace Roman Space Telescope aim to measure cosmic expansion, structure formation and dark energy with unprecedented accuracy. For these instruments, a 2 or 3% local bias isn't noise. It's a systematic error big enough to cloud entire results. By treating the basin around us as a calibration factor, rather than an inconvenience, future surveys can align local and global measurements more seamlessly. That means smaller error bars, fewer ambiguities, and stronger tests for any proposed new physics. The lesson is simple but profound. Understanding where we are is part of understanding the cosmos. The clearer our view of home, the better we can read the universe beyond it. The next wave of cosmological experiments will make environmental effects impossible to ignore. Instruments like the Euclid mission, the Vera-C, Rubin Observatory and the Nancy Grace Roman Space Telescope are designed to map billions of galaxies, trace the growth of structure across cosmic time and pin down the nature of dark energy. Their precision will surpass anything achieved before, but that precision cuts both ways. Even a small local bias will stand out. The underdensity around us, once a curiosity, will become a key calibration anchor. Velocity fields, redshift distributions, and background temperature maps will be modelled together rather than separately. The environment will no longer be a background detail, it will be part of the measurement pipeline itself. This integrated approach changes the structure of cosmological inference. Instead of subtracting local effects after the fact, future surveys will build them into the analysis from the start. That means better consistency between local and global measurements, and a clearer view of whether any remaining Hubble tension is truly physical. In a sense, the most advanced telescopes in history will also be the most aware of where they stand in the universe. For decades, local structure was treated as something to remove a source of noise in the clean equations of cosmology, but the shift underway is turning that idea on its head. Instead of being an obstacle, the underdensity around us is becoming a tool, a fixed reference point that future surveys can use to refine their measurements. This transformation reflects how cosmology itself is changing. Early experiments could afford to ignore local bias because their uncertainties were large, but with modern instruments capable of sub-percent precision, even the smallest systematic effect can no longer be brushed aside. A structure extending nearly 1 billion light-years isn't a rounding error, it's a real part of the data. Integrated modelling allows velocity fields, redshift distributions, and background signals to be analysed in concert. When the local environment is treated as part of the model, cosmological parameters can be inferred with fewer degeneracies and cleaner confidence intervals. What was once labelled as a nuisance is turning into a calibration standard. Understanding where we are is becoming as fundamental to precision cosmology as understanding what we observe. Future cosmological surveys will not simply correct for local bias, they will be designed around it. Mission planners already model the gravitational landscape near our location to understand how it will shape incoming data. For experiments like the Euclid mission or the Vera C. Rubin Observatory, a small misstep in this modelling could cascade through the entire cosmological parameter set. This solution is proactive integration, rather than treating the local underdensity as an external correction. Future pipelines will incorporate it directly into their likelihood functions and parameter inference. This approach allows velocity fields, redshift distortions, and background temperature patterns to be handled consistently, ensuring that local effect cannot masquerade as cosmic signals. It's a subtle but profound shift in how science is done. Cosmology is no longer pretending to observe from nowhere. It's acknowledging its vantage point and folding it into the analysis from the beginning. By turning local bias into part of the experimental design, these missions won't just measure the universe. They'll measure it with eyes wide open to exactly where we stand. As measurements grow more precise, the room for ambiguity shrinks. Once environmental effects are fully modelled and folded into survey pipelines, any remaining Hubble tension will become a cleaner probe of the universe itself. That's when hypotheses like early dark energy or modified gravity can be tested under the sharpest possible conditions. This is a major shift. In the past, environmental noise blurred the edges of competing explanations, but once that noise is measured instead of ignored, each hypothesis must stand on its own predictive power. If early dark energy is real, its signature will remain after all environmental corrections. If it vanishes, the tension was never about new physics at all. The same logic applies to other ideas from neutrino mass hierarchy to exotic couplings between dark energy and matter. Precision isn't just about measuring better numbers, it's about drawing clearer boundaries between theory and artifact. By tightening those boundaries, the next generation of surveys will do more than collect data. They will decide which ideas survive the scrutiny of reality. When cosmologists talk about measuring the universe, what they are really doing is measuring differences between what they observe and the theoretical baseline they trust. For decades, that baseline quietly assumed that our vantage point didn't matter much. But the presence of a vast underdensity around us has forced a rethink. If we live in a hollow, then the baseline itself must be rewritten to reflect that fact. This doesn't mean the laws of physics change depending on where we are. It means the interpretation of data does. Velocity fields, redshift distortions, and background temperature signals all weave together to form a new location-aware reference frame. Once this frame is built into analysis, environmental bias becomes part of the standard model of how we measure, not a side note to clean up afterward. With this shift, cosmology moves from treating the local universe as a nuisance to acknowledging it as a measurable, predictable component of the cosmic landscape. Future discoveries won't just emerge from distant galaxies, they'll also come from understanding the ground we stand on. The baseline has always existed. Now we're finally defining it with the precision the universe demands. Correcting for local environment narrows the Hubble tension, but it does not erase it entirely. Even after accounting for the underdensity surrounding us, a stubborn gap remains between early and late universe measurements. This is where the conversation shifts from local geography to the fundamental workings of the cosmos itself. Several theories aim to explain this residual discrepancy. They explore new forms of energy, subtle changes in gravity, or the properties of elusive particles like neutrinos. Unlike environmental corrections, these ideas go beyond measurement. They reach into the physics that governs the universe's evolution. To test them, cosmologists need a clean baseline, which is why local structure must be addressed first. Once the noise of environment is stripped away, any remaining signal has a much higher chance of pointing to something real. The next frontier is not about where we are, but about what the universe is made of and how it behaves on its grander scales. Among the leading contenders to explain the remaining Hubble tension is early dark energy, a short-lived energy component that would have briefly accelerated the expansion of the universe in its earlier stages. Unlike the familiar form of dark energy that dominates today, this early burst would have faded long before galaxies formed, but its influence would be etched into the cosmic background. If such an energy field existed for just a few 100,000 years after the Big Bang, it would have slightly shrunk the sound horizon, the standard ruler imprinted on the cosmic microwave background. That would raise the inferred value of the Hubble constant without conflicting with most other cosmological measurements. This elegant idea has gained traction because it fits the data well, but it comes with challenges. The timing and strength of the energy injection must be finely tuned. Too much early dark energy would disrupt the growth of structure. Too little would leave the tension unresolved. Even so, it remains one of the most active areas of theoretical research, a reminder that sometimes the key to the present lies in the first heartbeat of the cosmos. Another approach to the Hubble tension doesn't add new energy at all. It adjusts the force that drives the expansion of the universe. In modified gravity models, the strength of gravity itself can evolve slightly over cosmic time, changing how the universe expands without altering its contents. If gravity were marginally weaker in the early universe, expansion would proceed a little faster than expected. That shift would reduce the inferred age at recombination and raise the early universe estimate of the Hubble constant, potentially bringing it closer to local measurements. Unlike early dark energy, this explanation focuses on rewriting the rules of interaction rather than adding new components. The idea is theoretically elegant but faces stiff observational tests. Even small deviations from general relativity can ripple through structure formation, gravitational lensing, and the cosmic background. To succeed, these models must reproduce the precision of the standard lambda CDM model. While solving the tension, modified gravity isn't a guaranteed solution, but it pushes cosmology to examine its most fundamental assumption, that gravity itself hasn't changed since the beginning of time. A third avenue of research focuses on particles so elusive they pass through entire planets without a trace. Neutrinos. In the standard cosmological model, these particles have extremely small masses and play a modest role in shaping the early universe. But if their properties differ from current assumptions, they could help explain part of the Hubble tension. The key lies in how neutrinos affect the expansion rate. Heavier or more interactive neutrinos would slow the universe's growth, early on changing the size of the sound horizon at recombination. A smaller sound horizon would push the inferred Hubble constant higher, aligning it more closely with local measurements. Unlike early dark energy or modified gravity, this scenario doesn't introduce an entirely new force or field. It tweaks the behavior of a known particle. That makes it experimentally attractive because it can be tested not only with cosmic surveys, but also with laboratory experiments on Earth. If neutrinos are hiding extra mass or interactions, they may hold one of the cleanest keys to the cosmic expansion puzzle. Some cosmologists look beyond standard particles and forces to the mysterious dark sector itself. If dark matter and dark energy interact even faintly, the resulting dynamics could alter the universe's expansion history and help explain the Hubble tension. These models imagine a hidden exchange of energy between the two dark components. If dark energy was slightly stronger in the early universe and gradually transferred energy to dark matter, the expansion rate would have been higher in the past than currently assumed. That could shrink the sound horizon, raise the inferred Hubble constant, and bring the two key measurements closer together. This idea is attractive because it doesn't require an entirely new force, just a subtle coupling between components that already dominate the cosmos. But it comes with risks. Any energy exchange must be finely balanced, or it would disrupt structure formation and gravitational lensing patterns. The dark sector remains largely invisible, making it one of the most flexible and challenging frontiers in cosmology. If the tension hides here, it will take a new generation of data to reveal its signature. Among the more speculative possibilities is phantom energy, a hypothetical form of dark energy that grows stronger over time, pushing the expansion rate faster than the standard lambda CDM model predicts. In these scenarios, the equation of state of dark energy drops below -1, leading to accelerated expansion that intensifies with time. Such models can in principle ease the Hubble tension by allowing the present-day Hubble constant to be higher without changing early universe physics. However, this comes at a cost. Phantom energy often leads to theoretical instabilities, including scenarios where the universe eventually ends in a catastrophic Big Rip. Despite those problems, these models remain under study because they offer a direct way to shift late-time expansion. Even a slight departure from a constant dark energy equation of state can change the inferred cosmic timeline. Phantom energy is not the most elegant explanation, but it reminds cosmologists to keep the door open. Sometimes the universe reveals its secrets in the least expected corners. Another proposal sits between the stability of the standard lambda CDM model and the extremes of phantom energy, a time-varying or running dark energy. In these models, the density of dark energy changes gently over cosmic time rather than remaining constant. A slightly stronger dark energy density in the recent past would naturally lift the measured Hubble constant without requiring any violent behavior in the future. This idea has a major advantage: flexibility. Unlike early dark energy, which is confined to a narrow window after the Big Bang, running dark energy can adjust the shape of the expansion history over billions of years. That means it can be fine-tuned to fit observations from both the early and late universe simultaneously. The challenge lies in detection. The signal is subtle, buried in the small differences between cosmic distances measured at different epochs. Only the most precise surveys like the Euclid mission and the Nancy Grace Roman Space Telescope will have the sensitivity to confirm or rule out these variations. If dark energy is slowly evolving, the universe may not be static in its acceleration at all, just patient enough to reveal its changes gradually. A subtler way to adjust the early expansion history is to add extra light particles to the cosmic mix. These are sometimes called dark radiation or exotic relativistic species. If the universe contains slightly more relativistic energy in its earliest moments than the standard model predicts, the Hubble constant inferred from the cosmic microwave background would naturally rise. The effect comes from changing the expansion rate before recombination. More radiation means the universe evolves faster. The sound horizon shrinks, and the early universe measurement of cosmic expansion moves closer to what local observations suggest. This approach is attractive because it doesn't require modifying gravity or post-recombination physics. It only tweaks the earliest energy budget. The main question is what these particles could be. They might be sterile neutrinos, axion-like particles, or something else entirely. Whatever their nature, their effects would ripple through the background radiation. Big Bang, nucleosynthesis and structure formation. Future high-precision surveys of the CMB and large-scale structure will help determine whether this extra radiation is real or just another idea waiting to be ruled out. One of the more sophisticated proposals involves splitting dark energy into two components, one that behaves normally and another that evolves with time. These hybrid models attempt to combine the stability of the standard lambda CDM model with the flexibility of early dark energy, or running dark energy. In these scenarios, one part of dark energy dominates today, driving the accelerated expansion we observe, while a second component was active in the early universe. By shaping the expansion history at two different epochs, these models can simultaneously match early and late-time observations, a feature that neither single-component model can achieve easily. The cost of this elegance is complexity. Two-component cosmologies introduce more parameters, making them harder to test and easier to overfit. They also require careful tuning to avoid contradicting the precise measurements of the cosmic microwave background and galaxy surveys. Even so, this line of research is gaining traction. As measurements become sharper, hybrid models may offer a flexible yet testable framework for resolving the Hubble tension without breaking everything else we know about the universe. At this stage, cosmology isn't defined by a single neat solution. The Hubble tension has evolved into a carefully balanced puzzle with many moving pieces. Each hypothesis, from early dark energy to modified gravity, from extra neutrinos to hybrid dark energy, explains part of the story. None of them on their own cleanly closes the gap. This is why cosmologists rely on multiple independent lines of evidence. This sound horizon measured from the cosmic microwave background, baryon, acoustic oscillation data, local distance ladders and velocity field reconstructions all anchor different corners of the problem. When these anchors align, weak signals turn into solid conclusions. It's entirely possible that the final answer won't be a single breakthrough, but a layered explanation. Part environment, part measurement, systematics, part new physics. That's how progress often happens in cosmology, not with a single hammer blow, but with a steady tightening of the net around the truth. The puzzle remains unsolved, but it's sharper than ever. And in science, clarity is the first real step toward discovery. As the debate over the Hubble tension sharpens, a quiet revolution is unfolding in how we map the universe. Future observations will not only refine single measurements, they will weave together entire layers of data, galaxy positions, peculiar velocities, gravitational lensing, and background radiation. This multi-dimensional mapping marks the beginning of a new era of cosmic cartography. At its core is the cosmic web, a sprawling network of filaments, clusters, and voids that shape the motion of everything we observe. High-resolution surveys will reconstruct this structure with unprecedented clarity, allowing cosmologists to separate the local from the global, the environmental from the fundamental. Our position within this web is no longer an afterthought, it's part of the story. This shift transforms cosmology from simple curve fitting into detailed three-dimensional mapping. By combining the geometry of the cosmic web with precision measurements of expansion, scientists can extract signals that once hid in the noise. We are moving from sketches of the universe to full blueprints, and every new layer of data brings us closer to understanding how it all fits together. The cosmic web is not a metaphor, it is a real structure, a vast network of filaments and nodes spanning billions of light years with voids woven between them, Like the empty spaces in a giant tapestry, galaxies are not scattered randomly. They flow along these filaments, gathering in clusters at intersections where gravity has done its quiet work for billions of years. Until recently, this structure was only sketched in broad strokes, but new surveys are beginning to map it in exquisite detail. By combining redshift surveys, weak lensing measurements, and velocity reconstructions, astronomers can reconstruct not just where matter is today, but how it moves and evolves. This cartography does more than produce beautiful maps. It reveals the scaffolding on which cosmic history was built. It explains why galaxies cluster where they do, why the universe expands unevenly, and how local features like underdensities fit into the grander design. Every filament traced and every void mapped brings cosmology one step closer to understanding the full architecture of the universe. The cosmic web didn't appear out of nowhere. It emerged from tiny fluctuations in the density of the early universe, amplified over billions of years by gravity. Regions that were just slightly denser than average attracted more matter growing into filaments and clusters, while underdense regions expanded faster and became the vast voids we observe today. This process is governed by well-tested physics. In the lambda CDM model, gravity and dark energy shape structure formation like opposing hands, one pulling matter together, the other stretching space apart. Filaments form the connective tissue of this competition, channeling matter into clusters that act as the cosmic web's anchor points. Simulations show this evolution with striking clarity. A smooth, nearly uniform early universe slowly transforms into a foamy structure where filaments act like highways guiding galaxy flows. Our own region, a hollow surrounded by these filaments, is just one example of this vast pattern. Understanding how gravity builds this network is key to decoding both cosmic history and the role our local environment plays in it. Galaxies are not stationary beacons scattered in space. They move slowly but persistently under the pull of the cosmic web. Filaments act as invisible highways directing the flow of matter toward clusters and superclusters, while vast voids push galaxies outward as they expand. This constant drift is what gives the universe its large-scale dynamism. Velocity field reconstructions reveal these flows with striking precision. Streams of galaxies curve along filaments like rivers tracing a landscape converging where gravity is strongest. These motions aren't chaotic. They follow the underlying geometry of the web. Even the movement of our own galaxy reflects the influence of distant attractors and expanding voids. This understanding changes how we interpret cosmic expansion. Galaxies don't just sit passively on an expanding grid. They surf the gravitational currents of the web. To measure the universe accurately, astronomers must separate this motion from the smooth background expansion. Every galaxy is part of a larger choreography, one written not in stars but in the shape of space-time itself. Voids may seem like empty spaces, but they are far from passive. As the universe expands, these low-density regions grow faster than their surroundings, pushing matter outward and amplifying the structure of the cosmic web. In many ways, they act like invisible engines driving large-scale flows and shaping how galaxies and clusters evolve. Simulations show that voids expand anisotropically, not as perfect spheres, but as irregular regions responding to the pull of nearby filaments and attractors. This uneven growth helps stretch the web-feeding material into surrounding structures, while deepening the hollows themselves. Our own region is just one example of this ongoing cosmic dance. Voids are also powerful tools for cosmology. Because they are less affected by complex astrophysical processes, their shapes and growth rates are clean traces of how gravity and dark energy work. Studying their expansion offers a complementary way to probe the geometry of the universe, independent of clusters or supernovae. In short, voids are not the absence of structure. They are active players, silent but fundamental in the cosmic story. The filaments of the cosmic web form what astronomers often call the skeleton of the universe. These narrow, elongated structures are where most of the universe's matter resides, threading their way through enormous voids and connecting clusters like joints in a vast cosmic spine. Mapping this skeleton requires combining multiple observational techniques. Redshift surveys reveal the large-scale distribution of galaxies. Weak lensing exposes the hidden dark matter scaffolding, and velocity reconstructions show how galaxies flow along the filaments. When layered together, these techniques produce a three-dimensional map of how matter is organized on the largest scales ever observed. This skeleton is more than a structural curiosity, it shapes the entire cosmic evolution. Filaments funnel matter into clusters, guide galaxy formation, and even affect star formation rates by regulating how gas flows between regions. To understand the universe, it's not enough to look at individual galaxies. One must trace the invisible lines that connect them, the bones of the cosmos itself. Filaments don't just shape the large-scale architecture of the cosmos, they influence the lives of galaxies themselves. The thin streams of matter flowing through these structures feed galaxies with gas, setting the pace of star formation and the growth of stellar populations over billions of years. A galaxy's position within the web can determine its evolutionary path as much as its mass or size. Galaxies embedded deep inside filaments tend to grow steadily, fueled by a continuous inflow of cold gas. Those near nodes where filaments intersect experience more turbulent interactions, often colliding and merging with neighbors. Meanwhile, galaxies at the edges of voids evolve more slowly, starved of fresh material. These differences leave fingerprints in galaxy morphology, age, and chemical composition. This environmental effect is crucial for interpreting observational data. Cosmology isn't just about where galaxies are, it's about how their surroundings shape what they become. In the grand choreography of the cosmic web, filaments are not passive scaffolds. They are active supply lines feeding the growth of galaxies and the structure of the universe. At the intersections of filaments lie clusters, massive gravitational wells where thousands of galaxies gather. These crossroads are the densest nodes of the cosmic web, the places where matter has been flowing for billions of years. Their sheer mass makes them cosmic laboratories, offering insight into how gravity, dark matter, and baryons interact on the largest scales. Clusters grow by drawing in material along filaments. Galaxies' gas and dark matter stream inward, heating up as they collide and settle into the cluster's gravitational grip. This process creates hot plasma visible in X-rays, gravitational lensing arcs that reveal hidden mass and a dynamic environment where galaxies merge and evolve rapidly. These massive nodes also anchor the geometry of the web itself. Their positions trace where the universe's original density fluctuations were strongest. Studying their distribution helps cosmologists test the expansion history and the underlying cosmological model with high precision. In the grand design of the universe, clusters are not isolated islands. They are the hubs of an intricate network where everything flows and everything connects. Beyond clusters lies an even grander scale, superclusters. These colossal structures spanning hundreds of millions of light years are formed from webs of clusters and filaments woven together. They are not gravitationally bound in the traditional sense, but they shape the cosmic landscape through their mass velocity fields and gravitational pull. Superclusters act as massive gravitational basins, redirecting the flow of galaxies and influencing how voids expand. Structures like the Shapley supercluster and Laniakea supercluster illustrate just how vast these regions can be. Galaxies within them are not simply expanding away, they're streaming toward deeper gravitational wells, following trajectories that can be traced like cosmic river systems. Because of their scale, superclusters are powerful probes of cosmic geometry and dark energy. Their distribution reveals how structure grew from the nearly uniform early universe, and their velocity fields reflect how the expansion stretches space itself. Superclusters remind us that the universe is not only vast but structured. Their reach extends far beyond their boundaries, subtly shaping the motions of galaxies like ours. When viewed on the largest scales, the universe reveals something remarkable. It isn't random. Its structure is patterned, shaped by the interplay of gravity-dark energy and the primordial fluctuations left behind by the Big Bang. Filaments clusters, superclusters and voids fit together like pieces of a cosmic mosaic, each part influencing the others through flows and gravitational tides. This pattern isn't static. Over billions of years it stretches and evolves, with galaxies moving along filaments and voids, expanding like slowly inflating bubbles. The geometry we observe today is just a snapshot of a much longer story, one that began with tiny ripples in the early universe and continues to unfold in real time. Modern surveys are finally giving us the resolution to trace these patterns with precision. By understanding how they form and interact, cosmologists can uncover not just the shape of the cosmos, but the physical laws that built it. The universe is a tapestry of patterns, and learning to read those patterns is how we begin to understand its past, its present, and its fate. All the structures we've explored, voids, filaments, clusters, and superclusters, are more than astronomical curiosities. They are the physical manifestation of the universe's initial conditions, a code written in matter and space-time that cosmologists are only beginning to decipher. Each galaxy's motion, every stretched filament and every hollow region, carries information about what happened in the first fractions of a second after the Big Bang. This is what makes cosmology unique. Unlike other sciences, it cannot repeat its experiments. Instead, it reads a single vast experiment written across billions of light years. By decoding the patterns of structure, scientists can infer how the universe expanded what it's made of, and whether the fundamental laws have remained constant over time. Our position within this structure isn't a distraction, it's part of the text. Understanding it sharpens the way we interpret every observation. In the end, the cosmic web is both a map and a message, a record of what the universe was, is, and might yet become. We often speak about the universe as if we were outside it, observing from some privileged vantage point. But we are not. We are embedded deep within the cosmic web, inside a vast underdensity surrounded by filaments that stretch for hundreds of millions of light years. Our measurements, theories, and interpretations all pass through this filter, our cosmic address. This is not a limitation, it's a context. Just as ancient navigators learned to chart their position on Earth to cross the seas, modern cosmology must chart its position in the universe to read its signals correctly. Understanding our environment transforms raw data into physical insight. Every structure we observe, from the cosmic microwave background to the Hubble constant, is affected in subtle ways by where we stand. And by learning to correct for these effects, we reveal what lies beneath the true shape of the cosmos. In this sense, cosmology is as much about understanding ourselves, our place in the web, as it is about understanding the universe itself. Every science depends on perspective, but in cosmology, perspective is everything. We see the universe not from nowhere, but from a single specific point inside an enormous structure. Our observations are filtered through the lens of that position. Every redshift, every background photon, every measurement of expansion carries a faint imprint of where we are. By acknowledging and modelling this perspective, cosmology becomes more than a passive act of observation. It becomes a precise act of translation. What we see is not exactly what is, it is what reality looks like from here. Correcting for that vantage point brings us closer to the true geometry of the cosmos. This is why understanding local structure is not a footnote in cosmology, but a foundation. It ensures that when we talk about the age, shape, and fate of the universe, we're speaking a language stripped of local distortions. The universe hasn't changed our understanding of how to read it. The universe is vast, but the path to understanding it begins locally. By carefully modelling our cosmic neighbourhood, the underdensities, the surrounding filaments, and the flows of galaxies, cosmologists can strip away distortions that once blurred the global picture. What was once considered noise now becomes a crucial part of the signal. This shift mirrors a larger truth in science. Precision comes from knowing exactly where you stand, just as geologists must know the terrain beneath their instruments. Cosmologists must know the structure beneath their telescopes. Only then can they measure the true expansion rate, the real distribution of matter, and the shape of space-time on the larger scales. This is not a detour from cosmology's grand questions. It is the foundation for answering them. Every universal truth begins with local clarity, and as that clarity deepens, the gap between what we observe and what is real begins to close. For centuries, humanity has tried to understand the cosmos by looking outward, but modern cosmology shows that to truly see the universe, we must also look inward to our own position within it. Every observation we make is shaped by the gravitational contours of our surroundings. A clear picture of the cosmos depends on how well we understand those contours. This shift in thinking represents a quiet but profound change. Our place in the cosmic web isn't an obstacle to remove, it's an anchor to measure from. Once that anchor is well defined, the entire cosmic panorama comes into sharper focus. Expansion rate, velocity fields, and structural measurements stop contradicting each other and begin to form a coherent whole. This is the power of position. It turns perspective into precision. It allows cosmologists to move from debating conflicting numbers to uncovering physical truths about the universe itself. Where we are isn't just a detail, it's the key to seeing everything else clearly. Cosmology is a science of subtle signals. A shift of a fraction of a percent in the Hubble constant can spark debates that last years. A tiny distortion in the cosmic microwave background can change the way we model the entire universe. In a field this sensitive, context isn't optional, it's everything. Knowing the local structure transforms uncertainty into clarity. Once the gravitational effects of underdensities, filaments, and flows are accounted for, small discrepancies stop masquerading as new physics. The stage is cleared for genuine discoveries, not artifacts of where we happen to be. This is why the best cosmological surveys now build environmental modelling directly into their pipelines. They no longer treat local structure as noise, but as signal. Context becomes a lens, and through that lens the cosmos comes into sharper focus. Precision doesn't begin with the stars. It begins right here with where we stand. For much of its history, cosmology treated the universe as if we were floating outside it, gazing in. But modern science has forced a shift in narrative. We are not distant observers. We are participants measuring the universe from a single, very specific location in its web of structure. The story we tell about the cosmos must begin where we actually are. This realization doesn't make cosmology smaller, it makes it sharper. It replaces vague assumptions with precise modelling, turning what was once treated as background noise into a powerful source of insight. Our local environment becomes part of the equation, not an error to be brushed aside. By doing so, cosmology regains something it lost for decades: context. And with context, data transforms into understanding. The universe stops being an abstract set of numbers and becomes a coherent physical system with us inside it. This is the quiet revolution beneath the headlines, not just better measurements, but a better way of reading the cosmic story. Perspective may sound like a soft concept, but in cosmology it has hard consequences. A small misjudgment about our position can ripple through calculations of distances, velocities, and expansion rates. The Hubble constant debate itself has shown how critical these details can be. When the environment is ignored, the universe seems inconsistent. When it's accounted for, the pieces begin to fit. This is why cosmologists now treat perspective as part of the science, not a philosophical footnote. Our underdensity, the surrounding filaments, and the large-scale flows aren't just scenery. They shape the numbers we use to describe the cosmos. The lesson is simple but powerful. Where you stand determines what you see. This is as true for telescopes as it is for human experience. By grounding our models in our actual place in the web, cosmology becomes both more precise and more honest. Perspective doesn't distort the universe, it reveals it. The Hubble tension is often described as a problem, but it's more accurate to see it as an opportunity. Every mismatch between early and late universe measurements is a signal telling us something about how we observe where we are or how the universe itself behaves. What once seemed like an obstacle has become a lens. By embracing environmental modelling, cosmologists have already sharpened their tools. The uncertainty that once blurred measurements of expansion is now being transformed into a source of clarity. Each refinement peels away another layer of confusion, leaving behind the bare geometry of space-time. This is the essence of scientific progress, turning ambiguity into precision not by ignoring complexity but by understanding it. The local cosmic environment isn't the enemy of truth, it's part of how truth is uncovered. The path to cosmic clarity begins not in distant galaxies but right here with us. Humanity once believed it was at the centre of everything. Modern cosmology overturned that illusion, but now it's teaching us something more subtle. We may not be the centre of the universe, but our position still matters. It shapes what we see, how we measure, and the stories we tell about the cosmos. This isn't a return to geocentrism. It's the recognition that every observer in the universe has their own cosmic frame and no one's view is perfectly neutral. Accounting for that frame is what turns observation into true measurement. It's how the Hubble constant stops being a puzzle of contradictions and becomes a test of physical reality. By reframing our role not as outsiders but as situated observers, cosmology gains both power and precision. We stop pretending to look from nowhere and start measuring from somewhere, and that makes all the difference. The centre of the universe doesn't exist, but our centre, our vantage point, is real and essential to understanding everything else. In most sciences, experiments can be repeated from different locations, but in cosmology, there is only one experiment, the universe itself, and we observe it from exactly one point. That makes the observer inseparable from the measurement. Every photon we detect, every redshift we record, every expansion rate we infer carries the subtle imprint of our cosmic location. This is why modern cosmology increasingly treats the observer as part of the system, not an external onlooker. Position isn't an inconvenience to correct away, it's a variable to include. By folding our cosmic environment into the equations, what once looked like inconsistent results begins to align into a coherent picture. This approach doesn't make the science less objective, it makes it more honest. By admitting where we stand, we get closer to the underlying reality, rather than a distorted projection of it. In cosmology, the observer is not outside the experiment, we are standing right in the middle of it. Numbers alone don't build knowledge, they must be placed in context to form understanding. For decades, cosmology collected extraordinary measurements, background radiation, galaxy redshifts, expansion rates, but often treated them as if they were gathered from nowhere. Today, the discipline is learning to place those numbers back where they came from, inside a vast structured universe seen from a specific location. This shift turns raw measurement into real comprehension. The Hubble tension isn't just a statistical mismatch. It's a map of how perspective, structure, and physics intersect. By interpreting it through the lens of our environment, cosmologists are transforming confusion into a sharper view of reality. In doing so, the field returns to its roots. Cosmology has always been about reading a single universe from a single vantage point. The better we understand the vantage, the more truth the data reveals. Measurement is where the story begins. Understanding is where it finally becomes clear. As cosmology integrates local structure into its measurements, the fog surrounding the Hubble tension begins to thin. What once looked like competing truths starts to resolve into a single, clearer picture. The universe itself hasn't changed, our ability to read it has. This is the power of precision born from perspective. When the observer's location is treated as part of the data expansion rates, aligned structures make sense and discrepancies reveal genuine physics instead of measurement artifacts. What used to be a source of frustration is becoming a powerful diagnostic tool. In this way, cosmology is stepping into a new era. No longer just collecting numbers, It's learning to see those numbers in their proper frame. A sharper cosmos isn't one with fewer mysteries, it's one where the mysteries stand out more clearly against the background of what we finally understand. We have not solved every puzzle, but now we can see the edges of the pieces. For a long time, cosmology chased the deepest and farthest corners of the universe in search of answers, but clarity is not found only at the edge of the observable cosmos. It also begins right here in our immediate cosmic environment. By understanding where we are, we finally understand what we are truly looking at. The expansion rates, background signals, and structures we measure are all filtered through this vantage point. When we include it, the puzzle sharpens. When we ignore it, the puzzle fractures. The Hubble tension is the clearest proof of how much position matters in modern cosmology. This insight doesn't make the universe smaller. It makes it more real. The local environment is not noise. It's the first layer of the cosmic story. Without it, everything else is slightly out of focus. With it, the universe comes into view with remarkable precision. The search for cosmic truth doesn't begin at the edge of space. It begins here at home where we stand. The Hubble tension has often been described as if something in the universe were fundamentally wrong, as though nature itself had made a mistake. But the more precisely we study our position and its effects, the clearer it becomes. The universe was never broken. Our picture of it simply wasn't complete. Every underdensity filament and flow we uncover isn't a flaw in the data, but a piece of the framework that shapes what we see. When these elements are added back into the model, contradictions dissolve and the cosmos regains its coherence. This isn't just about fixing numbers. It's about understanding reality as it truly is. The story of the universe doesn't need rewriting. It needs rereading with better light, sharper lenses, and a clearer sense of where the reader is standing. In the end, the universe remains what it always was, vast, precise, and waiting for us to see it clearly. The story of the Hubble tension is not one of failure, but refinement. Each debate, each recalibration, each environmental correction has forced cosmology to sharpen its tools. The result is not just better numbers, it's a clearer understanding of how to measure the universe itself. By embracing our location as part of the experiment, cosmology has gained a level of precision unimaginable only a few decades ago. Modern surveys, sophisticated models, and careful treatment of local structure now allow scientists to strip away noise and reveal signals with unprecedented clarity. This shift will ripple outward. Every future discovery, from the nature of dark energy to the geometry of the cosmic web, will rest on the foundation built here, understanding where we stand and how it shapes what we see. Sharper tools don't just refine old answers, they reveal new questions hiding beneath the surface. What began as a source of bias is becoming a pathway to discovery. The local structures that once complicated cosmological measurements, underdensities, filaments, and galaxy flows, are now critical components of the analysis itself. By accounting for them, cosmologists have turned what once blurred the picture into something that sharpens it. This is a powerful transformation. It means the very factors that once obscured the Hubble constant may hold the keys to unlocking deeper layers of cosmic truth. Environmental modeling doesn't just correct measurements, it reveals how the universe shapes and responds to its own structure. Many breakthroughs in science happen not by finding something entirely new, but by looking differently at what's already there. Cosmology is in the moment now. The universe hasn't changed. Our way of reading it has, and that's enough to open new doors. Cosmology has always been an act of seeing, but true clarity comes not just from sharper telescopes, but from better understanding the view itself. A lens can be perfect, yet the picture will blur if the observer doesn't know where they're standing. Recognizing and modeling our vantage point has turned the Hubble tension from a stubborn puzzle into a refined scientific instrument. This is the quiet beauty of progress in cosmology. No single discovery solved the problem. Instead, countless small refinements in how we map the cosmic web model, underdensities and measure flows accumulated until the picture came into focus. Clarity in science is rarely sudden. It builds slowly like stars forming in a dark nebula, until the shape of the universe emerges from the noise. We didn't need to look farther, we just needed to see better. After decades of chasing discrepancies, cosmology is learning to see the universe with new clarity. The Hubble tension may not vanish overnight, but it has already changed how science approaches the cosmos. What began as a stubborn mismatch is becoming the foundation of a more precise and honest understanding of reality. The key wasn't just bigger telescopes or longer baselines, it was perspective. Once the local environment with all its structures and flows was treated not as noise but as signal, the fog began to lift. Expansion measurements aligned more closely. Models gained predictive power, and the universe itself came into sharper focus. This transformation is bigger than one number. It's a shift in how we observe, think, and measure. The cosmos has always been here. We're finally learning to see it for what it truly is. A clear universe isn't simpler. It's simply more real. In the end, the great revelation of modern cosmology isn't just about what the universe is made of. It's about where we stand within it. The Hubble tension was never merely a problem to solve. It was a reminder that we are not distant observers, but part of the story we're trying to read. Our local underdensity, the filaments that surround us, and the flows that carry galaxies across space are not footnotes. They are the frame through which the entire cosmic picture comes into focus. By finally acknowledging that frame, we've turned confusion into clarity and contradiction into insight. This is how science moves forward, not by pretending to be outside the universe, but by accepting that we are inside it looking out. Every measurement is a sentence in a much larger narrative, and every refinement brings us closer to understanding the plot. The story of the universe was always here. We just had to realize we were standing in its pages.